Hi everyone, my name is Manasa Kalanadhabhatta and I'm a PhD student at the University of Massachusetts Amherst. Today I'll be talking about FatigueSet, a multi-modal dataset for modeling mental fatigue and fatigability using wearable devices. This work was completed at Nokia Bell Labs with my co-authors Chulhong, Alessandro Montanari, and Fahim Kawsar. Before presenting our dataset, I want to talk about why it is necessary to manage fatigue in the first place. According to the National Safety Council, fatigue is estimated to cost employers about $136 billion per year in health-related loss of productivity. Mental fatigue in particular leads to reduced decision-making and planning abilities, reduced alertness, loss of memory, and increased risk-taking behavior. However, managing mental fatigue is extremely challenging due to a number of reasons. First, fatigue is a poorly defined construct. It includes experiential aspects such as subjective feelings of tiredness. In behavioral terms, fatigue is reflected as a drop in performance. It is also associated with neurophysiological markers such as a decrease in heart rate variability. Moreover, fatigue is often confused with related phenomena such as stress, boredom, or burnout, making it difficult to effectively identify and mitigate the effects of fatigue. Second, different types of fatigue, particularly its physical and mental manifestations, are closely interlinked. Mental fatigue is linked to worse performance on physical tasks, whereas the effect of fatigue due to physical activity on mental performance is less known. This interplay is often ignored in lab-based studies of fatigue, but becomes important to understand for the implementation of real-world fatigue management systems. Lastly, fatigue is generally quantified based on self-reported questionnaires, which may be biased due to subjective factors or may not reflect the behavioral component of drop in performance. In other scenarios, fatigue is instead measured directly in terms of performance declines or changes in physiological markers. This approach, however, inherently detects fatigue after it has had a noticeable effect on an individual's performance, and is therefore inadequate if we want to intervene before the effect is realized. Implementing just-in-time wearable fatigue management solutions requires us to identify physiological signals that can be early indicators of fatigue, and which can be measured in naturalistic settings. Given these challenges, we asked ourselves if we can characterize the effect of physical activity on mental fatigue in the real world. Specifically, we hypothesized that sensor data from wearable devices could be leveraged to explain the effect of physical activity on mental fatigue and resulting drop in performance. To formalize these concepts, we adopt a taxonomy that defines fatigue as the subjective feelings of tiredness and exhaustion felt by individuals. The term fatigability, on the other hand, is used to describe the corresponding decline in performance. We note that fatigue and fatigability are accompanied by various neurophysiological changes, which may be captured via wearable sensor data. In studying the effect of physical activity on mental fatigue and fatigability, prior research has proposed a number of theories. For example, the inverted U theory states that arousal from physical activity will lead to an improvement in cognitive performance. However, after a certain extent, further arousal will subsequently decrease performance. While there is empirical evidence refuting this theory as well, the general consensus indicates that the type, intensity, and duration of physical activity all play an important role, along with the kind of cognitive performance under consideration. In our work, we empirically investigate the impact of three distinct physical activity levels on two dimensions of cognitive performance. Mental fatigue and fatigability have also been associated with physiological markers such as an increased EEG alpha and theta wave activity and decreased heart rate variability. However, there is a lack of computational models of mental fatigue based on physiological signals from wearables. Our work is a step in this direction. We aim to bridge the previously mentioned gaps by means of a multimodal dataset that can be used for data-driven computational modeling of mental fatigue and fatigability. To this end, we collected wearable sensor data from 12 participants performing physical activity at various intensities in a controlled, fully reproducible setting. In order to be able to gain a comprehensive understanding of which physiological signals are the most important indicators of fatigue, we recorded sensor data from 4 different wearable devices at different locations on the body. The first device is a Nokia Bell Labs ear-able prototype, which is capable of collecting accelerometer, gyroscope, and 3-channel photoplethysmography data. Second, we use a Muse S headband to collect IMU and EEG data from the participant's forehead. We also used a Zephyr bioharness chest band to collect accelerometer, breathing, and ECG waveforms. Lastly, an Empatica E4 wristband was used to collect accelerometer, PPG-derived blood volume pulse, electrodermal activity, and skin temperature. You can see a study participant wearing these devices on the left. The rationale for using multiple devices was that there was little known about which physiological signals and which on-body locations are most valuable for characterizing mental fatigue. Our multi-device approach allows us to examine these research questions in detail by comparing signals from different devices. For this study, we asked participants to complete 3 sessions of data collection. Each session started with a 3-minute baseline phase where physiological signals were recorded at rest, followed by a fatigue measurement M1. Participants then jogged on a treadmill for 3 minutes at fixed speeds corresponding to low, medium, or high-intensity physical activity. Participants were assigned to one intensity condition each session with the order counterbalanced across sessions. The physical activity phase was followed by another measurement of mental fatigue and fatigability, which is denoted by M2. Then, we induced mental fatigue through a clinically validated 15-minute letter-numbered dual task performed on a laptop while seated. The dual task paradigm switches between a letter and a number task every 2 trials, and participants have to press different keys for vowels and consonants, as well as for even and odd numbers. This task induces more cognitive load than a single task and is validated to induce mental fatigue quickly. Finally, we measured fatigue and fatigability again at M3. Each fatigue and fatigability measurement phase, that is M1, M2, and M3, started with participants rating their perceived physical and mental fatigue on a visual scale. This was followed by a choice reaction time task to measure selective attention. In this task, participants are asked to respond to a black cross appearing at one of 4 locations on the screen by pressing the corresponding key. The CRT task is followed by a 2-back task to measure working memory. Here, participants are asked to press a key if the current letter on the screen is the same as the one 2 letters ago, and to withhold any response otherwise. Performance on both these tasks was measured in terms of response times. Each measurement phase took about 2 minutes to complete, and the measurements at M1 were used as a baseline for that session. In this manner, we built FatigueSet, a multimodal fatigue dataset containing approximately 13 hours of sensor data over 36 sessions completed by 12 participants. In addition to wearable sensor data, it includes fatigue and fatigability measures, as well as demographic and other trait information from each participant. Preliminary analysis of FatigueSet showed that physical and mental fatigue ratings increased following the physical and cognitive activity respectively, indicating that our experimental protocol was successful in inducing fatigue. However, no significant difference was found in response times on either the CRT or M-back task when all physical activity levels were pooled together. We then investigate the effect of physical activity on mental fatigue and fatigability by separating different levels of physical activity. First, we look at the change in mental fatigue and fatigability immediately following the treadmill session, that is, M2 minus M1. We find that medium intensity activity was associated with least increase in subjective fatigue ratings and slight improvements in performance on both cognitive tasks. Next, we look into fatigue and fatigability following subsequent cognitive activity after exercise, that is M3 minus M1. In this scenario, high-intensity physical activity led to a significant decline in CRT response times. These results indicate that the intensity of physical activity and the duration after the activity both impact mental fatigue and fatigability. There is an opportunity for wearable devices to utilize sensor data to characterize physical activity intensity, which can in turn be used to detect and forecast mental fatigue and its effect at a future point of time. To summarize, we hypothesized that physical activity impacts mental fatigue and fatigability, and that wearables can help characterize this effect. We collected a multimodal dataset for mental fatigue and fatigability and showed that physical activity intensity influences mental fatigue and fatigability both immediately and after subsequent cognitive tasks. We have made FatigueSet publicly available to promote research into multimodal sensing of mental fatigue while taking physical activity into consideration. You can find more details about the study in our paper or use the link on the slide to directly access our dataset. Thank you for your attention.